Okay, I think we will start. So, as I said before, if you have any questions during lecture, just raise your hand and I will try to stop and answer those questions at that point. Otherwise, I'm going to continue with introduction to Python and then go over to Numpy. And if we make it, we will also do math.lib. Otherwise, that will be for next week's lectures. Okay, we stopped with strings yesterday, and just to finish up, sometimes it could be interesting when you're programming Python to have to know what data types are actually assigned to a variable. And there is a special function in Python called type, which you can query this. So in this example here, I have 3 or 4 variables which I assign different values to, and we will be querying them to see what data types they have. So in this you can actually see the actual data types, and sometimes that could be interesting to kind of, if you have a code that you want to do different things depending on the data type, then you can use the type to query that and check to see or do stuff according to the data type. The next data type we're going to look into is something called a dictionary. And a dictionary is similar to a list, but instead of accessing the values in the list by the index, you associate the value with a key. So when you want to access the value, you give it a key, and also when you assign a value, you also have to assign it with a specific key. There is also a bit difference here that dictionaries, they use curly brackets instead of hard brackets. So please note of that. So that's the differentiates these data types. So in this case here, I create a new dictionary. It's called values. And values to dictionaries can be assigned like in a list directly when you create the dictionary, which is shown in the next example here. And here you see that we assign the first part here of the assignment is the key, and the second part is the value here. They are separated with a colon, and these key value pairs are separated with a comma sign. So here you have the curly bracket to start the dictionary and the curly bracket to end the dictionary. If we print this out, you see it looks like this. You access the values in a dictionary just like you do with a list. So in that case, it's not much difference. But the difference is that you access the values by their key name. So in this case here, if you look at David here, this is the value for David, and you access it by specifying the key David here. Same thing with Petra here. So now you get out the strings in this case. As with strings, all data in a dictionary can be any data types you like. So you can store floating point values, integers, you can store strings, booleans, lists, and other dictionaries. So it's a very flexible data type. You can also assign a value by assigning a specific index. So in this case here, I have values Peter here, which is a new, it's not part of the dictionary. And I put the key here, and then I assign the value using the equal sign here. So now you see here, I have a new Peter here added to the dictionary. Also note that the values in a dictionary is not created in the order which they were added. So they are stored in the way they are structured in the data type. So you can't count that they are listed in exactly the order you added to the dictionary. One of the nice things with dictionary is that it's very fast to find things in a dictionary. So when you have the key, you can really quickly check to see if they are in the dictionary. This is when you use, say, similar methods on a list, you will have to search for the list and check, and that is a linear operation, and it's much it's slower than when actually searching for an index in a dictionary. So in this case, we have a dictionary called IDX with 3 key value pairs, and if you want to check if there is a certain key exists in that index or dictionary, you can use the in operator. So basically you say Petra in index will return true if Petra, the key Petra exists in the dictionary. In this case here, Busse is not in the dictionary, so that should return false. So if we execute this, let's see what happens. So this returns true and this returns false. So in this way you can check for existence of certain values in a dictionary. You can check how many values you have in a dictionary by using the same methods that I showed before. So in this case, the .len method or function. This is wrong. It should be the len method or function. So in this case here, if I print len values, it will return the total number of values in my dictionary. So in this case, for the values, we had 4 key value pairs, so it returns 4. As I said before, you can adding stuff to a dictionary is just assigning new key value pairs like this. This will add values to the dictionary. So now I have Guido as well here at the end here. It's also possible to have dictionaries that consist of other dictionaries. So in this way, you can create quite complicated data structures with relatively simple means. So here I have created, for example, a configuration structure for an application of some sort. So on the top here, I have, this is the main dictionary here. And then I have several so the main dictionary has the keys general, constants, and items. And each of these have their own dictionary below them here. So this is the dictionary with the keys username and temp path that belongs to the general key value pair. So this is a dictionary. And this is also a dictionary. And this as well. And here you also see that I have a list inside my dictionary as well. Now you see the advantage of this structure here, that it's very flexible to access. I can access this by specifying config, and then I want to access the general section here, and then the key username here. So it's a nested structure here, but it's very easy to use. You see here, I can access the value. And here you have the values list here. I can access that with an index here to get out the number 2 value here. So it's a very flexible structure. It's also used in, when we get later on to storing data structures, there's a JSON data type that basically is exactly this nested dictionary structure in Python. So now we will go through most of the basic data structures of Python. So let's go in how we repeat stuff and do test for things like with if statements. And the first thing we have to look before we go into this is how code is structured in Python. I mentioned it early in my first lecture here that we need code is structured by indentation in Python. So I have a for loop here that loops over 5 values, and it ends with a colon. And when a statement or line ends with a colon, that means that there is a code block coming. So, and a code block means that you have to indent the next line to be part of that code block. So print here belongs to the code block for the for loop. And you can have multiple statements below here that belongs also to this for loop. So in this case, I can do print I times 2, for example. So now this print statement belongs to the code block. I execute this. You see 2, 4, 8, and so on. So if I had put this one here, it's not the same thing. So then I here is the last item from this loop here. So indentation is important in Python. You see here, as a print statement here does not belong to the code block for the for loop. I also recommend when you write code in your editor or your in Spider, set your editor for 4 spaces as an indentation. I also recommend not using tabs because it could be complicated to get it pretty correct. So my recommendation is spaces. If you use tabs, it's okay, but make sure that you only use one of these ways of indenting code. Because if you are not consistent when you do this, Python will complain a lot. So one example here is if I put a print statement with 3 here, like this. You see here that it complains here, unindent does not match outer indentation level. This is a very common thing you get when you have problems with your indentation or your source code. So the way to fix that is just make sure that you have consistent indentations everywhere. So we already looked at the loops, so we continue doing that. So if you want to repeat a given code block a number of times, you can use the for statement. And the for statement begins with a for, and then the variable you want to loop over, and then in range, that means over what values do you want to loop. So range will return you a kind of virtual list from 0 to up to 10, but not including 10, so 0 to 9. It's a bit odd that you have that, but it's sometimes you have to live with some of the oddities of languages. So this means that it starts from 0, goes up to 9. You can also provide a starting value and an end value. So then you have 2 arguments to the range statement, a range function, and then it will loop through up to 10, from 5 up to 10, because 11 is not included. It's also possible to have a step. So then you have 5 is the starting position, 21 is the end position, and 3 is the step length in the loop. Another nice thing with Python when it comes to loops or iterating over things or looping over, for example, a list, is that you don't have to have a special loop variable to access your elements in the list. For example, in many other languages like C++ or Fortran or C, you have when you want to loop over a data structure, you declare a loop variable, which you use to index another data type. In Python, you don't have to do this. You can loop directly over items in a list. So in this case here, I have a list with a number of items in it. So this is the list. And I can loop over this list without having the index variable. So in this case, I can do for value, which in values. So value here will become, for each iteration, value will be replaced by the value in this list, reference to this value. Let's see if we run this. So it just picks up everyone here and prints them out like this. Quite convenient when you want to loop over things and you process lines, for example, in text files or so on. You can use this to loop directly over lists. Of course, you can do the same thing with a loop variable. So in many cases, you need a loop variable anyway, and then you have to create a loop for that. And in this case here, I have two lists with value they're equally long, and then I can loop over these. So I define a loop variable I, which is has the length of a. It goes up from 0 to length of a, and that works because length will return you the length, which is 1, 2, 3, 4, 5, and range will only loop up until 4. So that works. And then I use the I to access my elements in my loop, like that. You can do this without the loop variables as well. So in this case here, I have two lists I want to access the element iterate over. And in this case, you have xpos and ypos. And then I can create two loop variables for x, y in zip x ypos, ypos. And then it can print out each of these without having to have specific explicit loop variables. So zip kind of combines these two lists into something that you can get out the values for. So for example, if I just print out okay, yeah, that was pointless. I thought it was more meaningful, but it wasn't. Okay. You can also iterate, of course, over nested lists. So in this case here, I have a list that contains several smaller lists. And if I loop here for p in points, that means p will be each of these lists here when I iterate over the outer loop. And for chord in p will get these values inside each of these one, in each of the smaller lists. So let's see what happens if we run this. So first I loop over this, I get 50, 50. I get this list, which I iterate here over in this, and then I print out each value in this in this statement here. You also see here, if I want to do nested loops, I have two levels of indentation here. So first I have the code block, outer code block here for this one, which contains these two statements here. Then I have the inner, so the outer loop will repeat this for loop here over a number of points here. And this one has a inner code block for this one here. There's another statement for repeating code blocks, and it is the while statement. So the while statement is also a loop statement, and it starts with a condition here, which must be fulfilled for it to be looping this code block. So while this statement is true, it will continue looping. In this case, I have a iteration here which I want to stop when the error is greater than something else here. So now it stopped when this was greater than the error. So that's one way of doing it. There is no do while statement. So otherwise, some languages have a while statement that goes the other way around. So you have a do, and then you have a condition that ends the loop at the end. This is not the case in Python. You don't have that. So this statement must, to start this loop, this has to be true from the beginning. So this condition, you have to kind of make sure it works from the beginning. Another statement that is important is the ability to do different things depending on different conditions. And that is like in a language, there is an if statement in Python. And it also works with the indentation. So in this case here, if I equals 0, then it executes this code block here. And then you have a variant of this that has an else. Then you have a code block here for if this is true. And this is the code block for if it's false. And then you can have else if as well. So you can have multiple conditions as well. So you have if this condition, this executes this code block. If I is less than 1, it executes this one here. If it's greater than 1, it executes this one. And then this is a final else here. So let's see here. If I change this to a negative value, doesn't print anything. So I see how it works. As with loops, you can also nest if statements. So in this case here, I have a condition here. If it's 0, then I execute this code block. But then I can have, if this is not true, do this code block. And here I have a code block that consists of an else if statement and an else if statement. So this is only evaluated if this is false. When we have looping iterating in loops, there is sometimes you want to exit the loop in different ways. You don't want the loop to continue until the end. And that you can solve with a while statement, for example, if you want. But in a for loop, it's possible to break out of the loop using the break statement. And so if you execute the break statement in a for loop, it will go outside the code block for the for loop. There's also possibility to continue to the next iteration by using the continue statement, and then it will just continue to the next iteration. Here you see I have it loops to 20. So if I equals to 10, or I equals to 5, it executes this block here, go to the next iteration. So it went to the number 6. And when it comes to 10, it breaks the loop. And then I'm after the loop here. So if statements, loops. Another part of coding is being able to define your own functions for implementing or modularizing your code or structuring your code in smaller parts. And in Python, this is done with functions. And functions are created by using the keyword def for define. And then you specify the function name. So here is the def statement. And then you have print doc. This is the function name. And then you must specify your arguments here for your function. And then you have a colon here again, because everything that is, when you define a function, the code block next is the function body. So in this case here, print here belongs to the print function here, the print doc function. You call a function just by specifying its name and adding parentheses at the end. So you always have to have parentheses, even if there is no arguments to the function. In this case, this will call the function. So this will call and print out this here. You can add parameters to a function. So in this case here, I have a print value function that has an argument a. And a can be used inside the function. So in this case, the only meaningful thing this function does is print out the value of a. So to use this function, I create a variable b, and then I pass this b along to the function, and it should just print it out inside here. It's probably obvious here, but the variable you specify here doesn't have to have the same name outside here. So you can provide any variable here to the function with any name. So another important thing is suppose you have a function and you use this variable inside your function, or for example, assign it a value. What happens? So in this case here, I have b equals 42 again, and then print b calls this function with this variable, and then I print b. Do you think b will change? Of course, you know the answer, but you can always execute the code here. So let's see what happens. So you see here, b is still 42. And this is the thing with Python, is that variable coming into to a function are passed as a reference. So they point to the data structure that you created in your. So b here is the data created is 42 and is stored somewhere in the memory of your computer. It comes into the function here as a, which is a reference to this 42. But when you do this, you actually create a new variable, new data here, 84, which a is referenced to. So there is now all of a sudden there is no connection between the incoming a and this here. This is a new variable. And variables created inside a function is never seen on the outside. So you can't ever access this outside the function. So in this case here, b is still 42. It points to the same data as a here. If you want something back from the function, you need to use something called return values. So in this case here, I have a function here. From math here, math is the math library in Python, and you can import it like this. When we come to NumPy, I will show you that you shouldn't use this kind of, but for now it's easier to use it like this. So I have a function f, which is returns the sign of x, and you return things out of the function using the return statement, and then you return the value out for the function. And in this case here, I have defined x and y, and then y is assigned the function value of x. So now you see here that y is returned from the function and assigned y here. If I don't return anything, so I just comment this out here and just do hello for the sake of it. So even if you don't use any return, all Python function will return something. And if you don't return anything, that something will be none. And none is a special variable or value that is means nothing. So you can also assign a variable to none, and it's basically that means just that you have the variable name defined, but it points to a meaningless data structure in memory. So it points to nothing. But this is what is returned when you don't use the return statement. So now it works again. And of course, you can nest this function here. So you could have done, for example, f of x here. That is also possible. So you can nest them definitely and use them in expressions as well. So next, now we have learned basically the most most important things in the language. So how you define your variables, what data types we have, how you repeat stuff, and how you also test for conditions in your code. But how do you organize your code in your program itself? So code is in Python is organized in something called modules, and modules are a collection of data types, collection of functions that are basically stored in a single file. And if you want to access these functions inside your own code, you use a statement called import. So in this case here, I want to use the math function in Python. Then I have to do import math. That tells Python that I want to access the built-in module math. And when you do this, you need to, it imports the module math with the prefix math. So all the functions and variables inside that module is accessed by specifying math dot like this. This is the cleanest way of importing modules because they don't interfere with other functions in Python. Because you need to prefix math before every function you call of this library. However, this is kind of inconvenient when you want to do math expression because you don't want to specify a prefix on everything you do in your code. So in this case here, you can use another way of importing a module, and that is using the from import construction. So in this case, let's say from math import, and then I have a star here. That means that import every function in the math module into my own code environment, or code block module. That means that all the functions are available without the prefix. So in this case, this is the same as above, but it's a bit more compact. You should try to not use this unless it's perhaps for math and for other math-related things that you don't want to prefix. Because you couldn't imagine that if you have a... Oh, I jumped a bit. So, for example, you could have your own, define your own functions, sine or square root or anything. And then if you import math, it will overwrite your own functions with the versions that are in the module. So that is something that, it could be other example that you have multiple modules with the same function names. And which function will be used depends on the order you import the modules. That's why the standard import statement like this is preferred, because then you make sure that if you import math, you need to specify math dot when you access the functions in that module. That means that it won't clash with anything else. If you don't want every function to be imported by the from state, you can actually specify explicitly which functions that are available or you want to import in the statement. In this case here, only square root and sine are available for you. So in this case here, I have yeah, and also modules, as I said before, it's very easy to create a module in Python. You just create a new source code file, an empty source code file, add all your functions for that module in that source code file, and then it's a module. So in this case here, I will create a file called prime.py, and prime.py will be my prime module. So it's for a module to calculate prime numbers, and the main routine I will be using is prime. So in this case here, I created a source code. It looks like this. I have my function here, and it returns you a prime. Now I have to do some tricks here to get it to work like this in a notebook here. If you're working in Spider, just create a new file in your same directory, save it there, and in your main file, you just import your function. It will find it automatically. In this case, I'm running on a cloud server somewhere on Google, so I need to upload my prime file here. So it is available in my current directory. So now I uploaded this to this current working directory. So now my module is available because it's the same directory. So now I can do import prime. Now you see I added a print statement here to, okay, there is a print statement here that prints out the prime statement here. So that's why it returned. And then I can access my, the print statement here. Sorry, the print statement here access the prime module and then the function inside this module. And this is a very simple way of actually structuring your code. If you are getting multiple pages of Python code in a single file, then it's probably time to structure it up into several Python files and then use import to access them. Then you get a small main algorithm, and then you can easily manage your other modules separately. Then there is one more thing I would want to mention is also that because Python is a scripting language, one of your source code file must be the main starting point, or just you have to start your program by executing one of the source code files. And in many other languages, there is the notion of a main program. For example, in C, you always have to specify a main routine, and that is the entry point to your code. So when you run your code, it will start by calling this main routine. In Python, the code execution begins by executing your source code file directly. But as I said, source code files can also be modules. So there needs to be some way to differentiate between a module and the starting point of a program. So in this case here, I have my prime module here again. I renamed this to prime extra with an added print statement. So in this case, it prints the special variable called name. So let's see here, I have to execute these two. So if I import this module now, this prime extra module, so this file now is called prime extra, contains this file here and the print statement name. So it will print out prime extra. So name will contain the module name if it's executed when it's imported. But now when you want to run this code, when you press play in Spider, or you type Python on the command line to run the code, this source code will behave differently, and the name will also be different. So when I run this prime extra now, you see it says main. So the same source code file, you can import it, and this becomes a module. If you run it, the name variable will become main. So that means that when you execute your code, that source code will be the main routine, so to speak. And if you want something special to run when it's executed like this, you need to kind of test if you're running it as the source code has to test if it's a module or it's run as a script. So in this case here, I have a main routine here that imports my prime. And you can see here I have an if statement here. So if name equals to main, then I know, okay, now this source code file has been executed directly by the interpreter. It's not imported, it's executed. So what do we do? Then we can call our routine like this. So in this case, if I run it by using the command line or pressing play in Spider, it will execute the code in the if statement. But if I import the same thing here, so if I import the prime main method or module, this code will not be executed. So in this way, you can have source code files that can be executed like scripts, but also imported as modules. So this is just a way of that you can check for if it's imported or not or executed. So usually when I have my main program in Python, I always do a special source code file that is my kind of main script file. And then in this file, I always have a if name equals to main. And in this routine, I actually execute my code, and all other modules will not have this. So I only have one module with this name equals to main. It's a bit complicated, but I think you understand it later on in the course. I just want to mention it here that, because otherwise, I mean, executing a Python script, you just Python and the script, and it will run all the executable statements in that file. This is just a way of differentiating between importing a module and running a module. Okay. I think we take a short break. Let's see, we meet back again at 13:15, and we look at how to format data. Okay. Make sure we record it as well. So formatting data can be done in multiple ways in Python. So if you use the print statement, perhaps you have tried it, it displays all the variables with the highest precision and the longest number of decimals. And in many cases, that is not ideal. And in Python 3, the main way of formatting data is using the format method of the string data type. And in this example here, I have 4 values again. And if I want to print those, I can use and create a template here, which each of these here represents a value going in here. So in this case, I have A, B, C, and D, and I want them to be represented by, so this first bracket here will be replaced by the first variable coming in, and so on. So if I run this, it will print out the values here with commas between them, like this. It is also possible to refer to the ordering of the variables in different ways. So if for example, if I have a specified number here, it means that I will use the 0, 1, 2, 3 as the value at that position. So in this case, my string is the first one here. So this is just by how numbers can be placed in a string. You can control different aspects of your string or your formatting using special commands here. So in this case here, the value will go in the bracket. The bracket will be replaced by the value. These here are just to indicate how where the string ends and begins. So in this case, I have set 15 here, means I want to use, it can't be longer than 15. And the output will be 15 characters in that bracket. So you see here, it will print out Python 3, this string here, in a field that is 15 characters long. So this here is 15 characters, and Python is printed on the left side here. You can control the alignment by using the greater than pointer here. So in this case here, I add a greater than sign here. And that means that it will be right justified. So now the Python string, it goes on the right side, and also the field width is still 15, but you put the string on the right side. You can center your data as well by using the, I don't know what this is called, the raise to operator. It should be point to the middle, I think. So that's why it's like that. And now it should center the string inside the field here. So now the Python is in the middle here. It is also possible to fill, instead of using spaces for filling the spaces between the string in the field, you can actually specify the character which you want to fill your field with. So in this case here, I have an underscore. I want to center the string, and it should be 15 characters wide. So if I run this, it fills, instead with spaces, it fills with underscores here instead. Quite convenient. So when you, for example, if you have a finite element code that runs your analysis and you want to do a result reports, all of these methods of placing strings can be used to create a nice report that is nicely formatted. So this was strings. Of course, we want to format other data types as well. So we have you can specify that by using special characters. So in this case, D means that it's an integer. And so colon D here, that means that I want to print an integer. And of course, that becomes 42. Same thing here, I can add a field width here. So you have I want the field width of 10 character, and it should be, this is an integer. Then I have a right justified 10 characters, left justified 10 characters, centered and filled with special characters. So these are the different outputs here of my integer formatting. Floating point is very common in simulation codes. Those can be controlled with there are different placeholders. So colon F is for floating point. Colon E is also a floating point with the engineering notation. In this case here, I can specify the field width of 10, and .2 here means 2 decimals. And this is 4 decimals, 6 decimals. And of course, you can use left justified and right justified as you want as well. So 2 decimals, this is 10, 4 decimals, and 6 decimals. And you can use scientific notation as well. So this is, it tries to use the best, and also the same thing goes here. So it uses 2 decimals, 4 decimals, 6 decimals. It's also possible to use name your placeholder. So you can think of this string here that you use here as a template for what you want to print out. So in this case here, I want the parentheses here, and then I have my first X value, Y value. So this will be, put my X value here, put my Y value here, and then in my format statement, I can specify X and Y directly like this. And one other really cool feature is that you can use dictionaries in the format statement. So if you have a dictionary with name keys, you can use the keys in the placeholders to format here. So in this case, I have params here. The only thing that is a bit is you have to use this kind of, you have to put 2 stars in front of the parameter here in this case to use it. But then it takes value 1, places that here, value 2 places it here, and value 3 places it here. Really nice. Sorry. Another secret that is well hidden is that everything you store in Python, all the variables that you create are all stored in dictionaries in Python, which And you can actually look at which these are by using the globals function in Python. That returns you all the variables. Let's see if I can add a just an illustration of this here. So if I just print globals, you can see here you get the dictionary of every variables that are defined. Here in this case I have Petra, kilo, and also so on. And what you can do with this is really easy formatting. So if you have value 1, 2, and 3 as variables, then I can print them out by specifying them in the format statement like this, and just providing the globals instead of the dictionary I had before. And it prints out like this. So that is a short introduction to formatting your data. And that is really important when you start doing text files that should be your results from your code, that you can do tables and all that printing in a very formatted way so the user can read it easily. Another important thing you have to do in programming is often that in simulation codes is that you need to read and write files. So for example, your finite element code perhaps has an input file defining the input to finite element code. And when you have done the simulation, you have to run the simulation again and write the data out to disk, the results, for example. So if you want to create a file, there is a special function called open. And what open does is it creates a connection between a physical file on your computer and returns you a special object which you can use to write or read from that file. So in this case, I tell Python here, open a file, myfile.txt for writing. So this string here tells Python it should write to this file. And the return here is an object that actually points to this file on the disk and enables you to write to that file. So in this case here, first I have to open the file. And then I can use special methods on this object. For example, text.write here. That means write text to this file. So in this case, it writes filens innehåll. And this is written on the same row. So write doesn't have the same functionality as print. So when you do print, it will go to the next line by default. Write will not, it will just write the character file, but doesn't do anything on new lines and stuff like that. So if you want to have multiple rows, you need to add \n to your row. Let's see here if I write this. So now the file has, the object has written this to the file. And when I'm done writing, it's very important that I actually close the file. That tells the operating system, I'm done with working with this file. And the operating system knows this and can actually make sure it writes to the disk, because many operating systems don't write directly to the files. They kind of cache it in memory to make it faster. And when you are done and you close the file, it actually in the background writes to disk. And when you do close it, you will make sure tell the operating system that this file is done. And just to see that it works, I can just here is this exclamation mark means that I'm going to execute a system file on my running Python instance in the cloud now. So in this case here, cat means print the contents of my file. So now you see here, this is what was written. So the file filens innehåll, this was written first. The next write statement wrote this part here, and the \n here, which is a new line. And the next row, the next line here was written like this. Reading from a file is basically just the same. We need to create a file object that points to the file on disk. But instead of using W here, I just put R instead for read. Now I open the file that I created earlier. And then there are multiple ways of reading a file. The simplest is just to do a read. And the read method reads the entire file into a string and returns that here. So content here will be a string which contains the entire file. And the same thing, it's important that I close the file. So now you see here, I got the entire file like this. There is a problem with read because in many cases when you use simulation codes, you have gigabytes, terabytes of data. And it is not very efficient to read a terabyte of data into a string. I don't think it's possible. I think your program will crash. So read should be mostly used for simple things or smaller files. So for smaller or for larger files, we need to do something else. In this case, there is a method on the file object called .readline, and it does what it says. It just reads one line. That means it reads a line with a character return and returns that as a string. So line by line in a text file. So in this case here, I open my file, read again, and then I do read line here, and it returns a string here, line. And now I use a while statement here to, so if there is no more lines, line will be empty, and then I don't have to continue. So in this case here, first I read the first line, and while the line is not empty, I continue to read by just calling read line repeatedly. And then when I'm done, I just do read file closed. So now you see here, I read the first line, I printed it out, and I printed the second line. And now the print statement always adds a character return to the printing statement. That's why I get 2 lines, 2 rows here, because the red line from the file contains a \n, which is a view line, and then prints add another one. So I get 1 and then an empty row and then the next line here. I can avoid this by using what we learned last time, the R strip here, which means I will remove the trailing stuff on the end of the string. That means it will also remove the \n. So in this case here, you see here, now it prints correctly here. So now it doesn't do double line returns here. Another cool thing is you don't have to use readline. You can actually iterate with a for loop directly over a text file. So now I open a text file, I do for line in text file, print line R strip. So you can treat it like a list and just iterate over the text file as a list. Works exactly the same. And if you know that you want to have your entire file as a list of lines, it's possible to use the read lines method. And read lines reads the entire file and returns it as a list of lines. So now you see I got the list back here with the first line and the second line. Nice. So to finish off this lecture here on the Python part, to make sure that you always call close when you are working with files, there is a new construct called with that makes sure that it always closes the file. So in this case here, instead of using an open statement directly assigning a text object, you do instead with open as text file. This will create the the file object text file, and you can do the normal operations here, reading the stuff in. But before it goes out of this code block here, the with statement makes sure that the text file object is closed. So it's a way of ensuring that you always close your files without remembering that you have to add the .close method on the text file object. I think let's see here. I skipped error handling here. You can read it on your own. I will continue now to the Numpy part. So, so yesterday and today we talked about the built-in data structure of Python, and you could create matrices with lists and dictionaries, but they are extremely inefficient when you need to work on large sets of numbers. For example, matrices and vectors. And that was realized quite early on in Python development, and there was a project called Numerics, which implemented matrix and vector operations, special data types for that for NumPy, or for Python. And that has continued to develop in different libraries. And what has become the de facto standard now is something called NumPy, or numerical Python. And it's an extension that is not part of the Python standard from the beginning, but basically it's the most used extension for numerical computing. It can be compared to the matrix data type in MATLAB. So it can do most of the things that MATLAB can do, and it's extremely efficient. So if, for example, if you use the Anaconda distribution for running your code, the NumPy built into Anaconda is based on the Intel math kernel libraries. That means that they implement matrix operations extremely efficiently. And also, if you have multiple cores in your machine, matrix vector operations will probably be executed on multiple cores. So it's extremely efficient data structures, and also library. So NumPy, as this is a special extension library, you need to import it to be able to use it. And there is a convention of doing this that makes sure that you have the benefits of not having to do too much prefixes, and also not having to type NumPy before everything. And the common way of importing NumPy is this statement here. So import NumPy as NP. That means that all your NumPy functions will have the prefix NP dot, but it's still that also separates it from tells your readers of your code that you're using NumPy. This is a NumPy function, so it's a good idea to do it like this. It's a bit larger library, so it takes some time to import. The basic object, or the foundation object of a NumPy, is the array object. And the array object stores a single data type as a continuous block of values in memory. So it can be a floating point, but the array must only consist of floating point values. So it doesn't have you can't mix floating point strings and integers in the same data type or object. So that is a limitation, but also makes it really fast for computational use. So when you allocate a NumPy array, it will be a continuous block of memory in your computer. Creating objects is done, or smaller objects is done by using the mparray function that will return you an array object. The first parameter here is the actual structure of your object. So in this case, this will be a vector of 3 elements, and it's a floating point vector. And when you print an array, you can always see it will denote the floating point with dots after the values. And if you don't specify any data type at the end here, like this, NumPy will try to figure out what data type it is, because everything in Python is a data type. So Python can query, okay, this list, for example, only contains integers. So then he probably wants an integer array as well. And if you specify floating point, you will get the floating point array. So it's quite intelligent. You can also have multi-dimensional arrays, and then you give it a nested list like this. So this is the first row, this is the second row. And then the same thing here, you have first row, second row, like this. So this is a floating point because I have a float here. This will be an integer because the data inside this declaration here is integer. There is also something that could be have to explain around storing things in computer memory. So an operating system, when you ask it for, I want memory, you will get a pointer to a contiguous block of bytes in memory. So everything in a computer, there is no notion, there is no two-dimensional things. Everything is one-dimensional. So an array is actually interpretation of a linear stored block of memory. So Numpy, when it stores things in memory, it stores it row-wise. And that is also because Numpy is implemented in C, and C also stores all its arrays row-wise. Fortran, which is also a very heavily used language in computational codes, stores column-wise. So there is difference here, and you can create both kinds of storage schemes, but by default it uses the row-wise storage. That means that in this case here, if I have a array of 6 by 5, it's stored like this, row-wise over the array like this. So in memory, all the data is stored in one single row, like this. So the actual two-dimensional structure is something we create. It's just a way of getting to the right position in this continuous memory allocation or memory allocated memory. When you have created arrays, you can query them for what kind of shapes there are with the shape property. So in this case, I just print the shape here, and you get the data back from the shape of it. So in this case here, I have, this is a vector, so it's 4 elements. This is a two-dimensional array, and it has the shape 2 rows and 2 columns. And then this is a 3-dimensional array. It has 2 columns, 2 rows, and 2, the next dimension here. So for example, if you have a function that comes with an array that is has a parameter that's an array, then you can query that array for its number of rows and columns by using the shape attribute like this. So in this case here, it will print 2 by 2 here and assign R2 and C2. There's another attribute to query the number of dimensions of an array, and that is called ndim. So in this case, B is a 2-dimensional array, so it's 2 in this case. There are multiple properties you can query. You have the dtype property, which actually returns you the actual data type of the array, the size, the number of elements in the array, and also the item size of each element in the array. And we can run this here. You can see here that the shape is 2 by 2, dimension is 2, and the data type is integer 64. That means that the integer consists of 64 bits in memory. And the item size 8 here, that means that is 8 bytes in size. That means, so if each byte is 8, that will mean that is 64. And the size is there is 4 elements in total. So with all these attributes, you can query the array in different ways and take decisions on that. You can change the shape of an array, and as long as you don't change the number of values in an array, it will not reallocate memory for it. This is a function that I will use to kind of illustrate the memory allocation. So memory will return the actual address of memory in your computer. So here I have let's go to clear. A 2 by 2 array integer. and I will print the memory of that. And then this in the second part here, I will reshape it to 4 by 1. So 4 by 1, that means that it's still 4 elements. And if you look at the array here of these two here, the memory address is the same, but now they're interpreted in 2 different ways. So the first A is 2 by 2, and A flat is 4 by 1. So they both of these point to the same memory location in memory, but have different shapes. What we can also do, this is really important. So we've talked about referencing in Python before, that everything is a reference to anything, and it's even more important when we come to Numpy, because Numpy goes to extreme lengths to not reallocate any memory, because reallocating a large block of memory is costly, and you want to really avoid that. That means also that compared to many other things, you can actually change values in an array by assigning them. Like, so for example, here I say A row 0, column 0 is 42. And now we come into something also. Indexing in Numpy is 0-based. So if you're compared to MATLAB starts have a 1-based indexing, but Numpy is 0-based. So what happens now here, if I assign 0, 0, which is 1 here, this one here, it will actually also assign A flat. So A flat and A points to the same memory location in memory. So if you modify one, the other one will also be modified. If you don't want this, if this is something that you want to avoid, you should use the .copy method. Same thing as we did with the lists before. So in this case, C equals to A copy. That means I copy A. And in this case, you will not, there will also, you can see also here that the memory addresses of these two structures are different now. So this is the same we had before, and now we assign 84 here. Let's see if we can just print A here again. It's much more illustrative. So A wasn't changed in this case. So we can also, let's see here. You can change the shape in different ways. So as long as this, in this case, I change it to a vector. So it's 8 elements directly, and I also have 4 by 2, like this. But that doesn't mean, so this one here is 2 by 4, and this is 4 by 2. But this is not the same as the transpose operator. So this here is just reshaping it, and this is actually doing a matrix transpose. So this is compares to a matrix transpose. You can also, of course, change the size of an array. And in that case, it will change the size and reallocate your object. And it will try to retain all the values that are existing in the array as much as possible. So if you shrink it, of course, the values will disappear. But if you extend it, it will kind of fill the array with the existing values. So here I have a 2 by 2, and then I resize this one to 9 by 9, and you see here it fills this array with the existing values from this first one here. Same thing with 4 by 4 and 4 by 2. So it reuses all the values that are inside the first one. And now these are newly allocating memory. So they are not pointing to each other. They are referencing new memory, which is important to think about. So let's see. Sorry for moving around here. So in many cases, creating arrays like we have done as up to now is really inefficient, because you don't want to send a list over to the array object unless it's very small array. So in many cases, you want to create empty arrays with different sizes. And as with MATLAB, you have this option here as well. So in this case, there is a function called np.zeros, which creates an array with certain dimension filled with zeros. You can do that with a data type as well. So you have the same options as you have with creating arrays as we did before. You can create arrays filled with ones. So you use np.ones function, and then you get an array filled with ones. If you want to assign a specific value, what you can do is actually create an empty array with an array with ones, and then just multiply by the value you want to assign it to. So in this case, the multiplication operator will be element-wise, so corresponds to the dot multiply in MATLAB, and multiply every element with 42. So that is a way to quickly assign values to every element in an array. As with MATLAB, you can also create array ranges to access specific parts of an array. Range is similar to the range command in Python. So creating a series of numbers that are increasing, for example. So MP range will create an array going from 0 to 9, like this. And using the reshape method, you can actually create arrays with a series, multi-dimensional arrays going from 0 to some part here. So in this case, I have a range with 100, and then I fill a 10 by 10 matrix with numbers like this. So first, this will be a long sequence from 0 to 99, and then I reshape it to 10 by 10. And then I create this kind of array. Also note that this here creates the memory area, and the reshape function, because it's still the same number of elements, it's okay to, there will be no reallocation in this reshape statement here. It will just interpret the array as a two-dimensional array instead. And you can, of course, specify the data type as well. And you can also specify going from -10 to 9, for example, with a step 2. So it has the same arguments as the normal Python range function. You can also create identity arrays, which is commonly used in linear algebra. So basically having a 10 by 10 with ones going on a diagonal like this. Range is not always the most optimal way of creating a linear interpolation of values, because it has distinct starting points and endpoints. But if you want something going from a certain number with some certain steps and a linear variation between, you can use the Linspace function instead. So in this case, I have a range here going from 0 to 1.0, and I want 10 values of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values, and it goes from 0 and 1. So The 0 and the 1.1 are guaranteed to be part of this array, and you always get 10 numbers. This will be used similar to the 0 point, the constructor when you plot things in MATLAB. It's very similar to that, and we will also use that when we look at the matplotlib library. And here I have 20 values. It's also possible to do expressions with arrays. So all these arrays can be, you can combine with normal operators in different ways. So in this case here, I have a array 5 by 5. If I do a plus 3, it will do element-wise addition on this array. If I do multiplication, we did that before, it will multiply all values by 3. And I can execute, so Numpy has all the normal math functions of Python are implemented in Numpy. So, with the difference that they can take arrays as input. So in this case, if you do mp.sin_a, the sin_a will be evaluated on each element in the array. So in this case, sin_x for every element in this array I created before. You can negate the array just by adding a minus operator before the array. You can add two arrays together. And you can actually add, they don't have to be exactly the same. And the operations will, if you have a smaller array adding to larger, it will be repeated on a larger array. Like this. So the only data structure we talked about now is actually arrays, and that is a generic data type. It actually has nothing to do with matrices. You can do matrix operations, of course, but you have to do that as separate functions. There is a data type, I will come to that a bit later here, that is a matrix object, and that you can do linear algebra with. But if you want to do linear algebra operations on arrays, you need to use special operators or functions to do that. So in this case here, I have a 4 by 4 array, and I can do a matrix multiplication by calling the dot function here. So a dot a will be a multiplied by a. I can also use the @ operator to do matrix multiplication. I can also slice and create subarrays from existing arrays. So first, okay, we start by how do you index an array. So indexing arrays, use the bracket operator just like you do with lists. And if you want to access the third element, I do A2. And if I have 2 dimension, I have a comma between the indexes here to access the row number 2, column number 3. You can assign arrays in the same way like you do this. So in this case, you have index here, and the value you can assign like this. So here I assigned 0, 1, 2. So this one was assigned 1 by 2. So it's row 1, this one here, and column 3. So 1, 2, 3. This is here assigned like this. You can also access subarray or slices by specifying a ranges between in these brackets, start, end. That will extract values starting from start up to, but not including end, so n minus 1. Start colon, it's the same syntax as for lists, so it's very similar. So here I do A 1 to 5, so that starts from 1, 2, 3, 4, but not 5. So this one is not included. This is the range I extracted here. Also very interesting thing here, when you do slices extract slices from arrays. Numpy will also try to avoid reallocating. So what you get back when you do a slice is actually a reference to part of the memory that's already been created. So what you get back is not newly created memory. So let's see here an example here. 8.5 here. So memory of A is 265360. And you see, and then you have an index here 368 here. So it's a bit shifted to the side by 8 actually, because floating point consists of 8 bytes. So it's 8 bits shifted here. But if you look at the memory here, it's part of the same memory address. So it avoids actually doing any copy. But then you have to be aware of modifying B will also modify A. So because they point to the same memory location. So here you see modify both of these arrays. Here are some examples of sub-ranges here which you can create. I will not go too deep in depth of this, but here you can extract different kinds of parts of an array. Here is also you can have every other column and row. It's also possible to mix different data types when you assign stuff. So this is perfectly legal here. So if B is a row in an array, if you assign a row, you can assign a list to that row. It doesn't have to be a array data type to be able to assign a row. So that works perfectly. And you can always see that when you create an array, we put a list as an input to the array argument, and that will be converted to an array. So you can mix and match lists and arrays where it's suitable. Yeah, there are also methods that you can use on the arrays. So for example, you have sum that can sum up an array. That sums all the values in the array. You can also sum on columns and rows, like this. Same thing, you have product. So you can do product of an entire array, and you can do it on each row. And finally, I'm a bit over time here, but I'm just trying to be quick. Matrix object. So there is a special object called the mp.matrix, which behaves like a matrix. So, and it also contains a certain methods and attributes that offer you, for example, in this case here, a.t, that means transpose. So that returns you the transpose of A. The normal multiply operator can be applied, and that means that it's a matrix multiplication. .I, matrix inverse. Let's see, there's stuff here. Yeah, there is also, like in MATLAB, you can save math files. NumPy equivalent is something called NPY and NPZ files. And there is an mp.save method function that can save any array to a file. Let's see here. So now you see it created 2 files, so XMPY and YMPY. And those can be loaded by using the load method. And you see here I got this output here. And you can also use a file object. So you can, if you want to store multiple of these objects in a single file, you can open a file, and then instead of providing a file name here, you can provide an object, and it will add to that file all the time. So each save will add an object. And you have to, if you want to read it again, you have to do the opposite direction again and load them in one after another. So let's see here, if we save these here, load them. Yeah, they came back from disk. And finally, there is a way of solving equation systems like A equals to B. You can do A, B, you can do solve here to solve for X like this. that is part of the np.linarg.solve function. Calfem for Python has its own special version that's called solvec, which is similar to Calfem, and I will go through that next week. So next week I will also look at go through matplotlib. I couldn't fit it into these lectures here, but you're of course welcome to look at the matplotlib lecture as well to plot stuff. So, any questions? You're of course welcome to send questions using Canvas as well, or send a message to email if you want. So I will put this lecture up as a video shortly. It takes some time to process these, so have some patience. It will be early in the evening, I hope. Otherwise, I will close this lecture. So goodbye. I hope it works this time as well.